Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome. This is the second lecture of first week. Let us continue with what we were discussing in the first lecture. You see, in the first lecture we had seen that in engineering analysis of any physical system, first we need to have a simplified model of the system, and then once the simplified model we have, then mathematical model of that ideal system is to be written, and then finally those mathematical models need to be solved. In most of the problem we come across in real life, these mathematical models are expressed in the form of partial differential equations. Okay. Now, again, for most of the problem we come across in real life, solution of these mathematical models are not very straightforward. We cannot have the closed form solution. That is maybe because of the entire system cannot be represented through a single equations, or sometime because of the boundary conditions, non-linearity, complexity associated with the domain, we cannot have a very straightforward solution of this mathematical model. So we need to go for a numerical technique, and finite element method comes in there. So finite element method is a technique, numerical technique, to solve those partial differential equation, which is essentially representation of some physical system. Now, we also had introduced a concept of approximation in the context of analysis. And what is that? What is the meaning of the approximation? You see, when we say physical system and then model and then representation of the mathematical representation of the model and then finally solution. So every step actually we approximate. Our idealized system is essentially an approximation of the physical system. Mathematical representation is an approximation of the mathematical approximation of the physical system, and then finally when we solve those equations in the solution also we made approximation. So what essentially we look for an approximate solution of a physical system. Now when we say approximate solution, it cannot be anything for the system. This approximation should be as close as possible to the real system, but then how close it is to be, that depends on the context of the analysis. What exactly you look from the analysis, depending on that approximation needs to be done. Okay. Now, in order to demonstrate that, you remember we took this example of this determination of circumference of a circle. Now, I will not go through the entire example once again, but then I would like to re-emphasize the points that we understand from these examples. One important point is that if our physical system is complex, we cannot solve the physical system, cannot have a solution of the system as a whole. We can break the system into small subsystems. We can break the domain into small subdomains, like we have done here in case of this example, where the entire circle is represented by piecewise linear segment. And how many linear segments, that depends on what accuracy we want. If we increase the number of such segments, we have better accuracy. Okay. And then once we have divided the entire problem into small sub-problems, such that for every sub-problems we have certain level of understanding, we know we can express the governing equations, then after that we assemble we add all these subproblems to get the information about the entire system. So that is the main outcome of that we understand from these two examples. Okay, and another important point is if we keep on increasing the number of such segments, we get better accuracy. But then for an infinite, in order to get an exact solution, your number of segments should be infinite, because it is an infinite collection of infinite number of points. But then it is, we don't deal with that so many that large number of segments, right? We divide the entire circle, divided the entire circle into finite number of segments, and each segments having finite length, right? And that gives an approximation which is acceptable for us in the context of this problem. Now, with this understanding, let us see these realization, these outcome essentially constitute the premise of finite element method. Now, with this understanding, let us see at least the concept of finite element method. Okay, take an example of a plate with a hole at the center and subjected to in-plane tension. This is a very classical problem, and if you have taken a course on elasticity, you might have seen the solution of this problem. Now, let us to start with remove the load from the system. Now, this is our actual system. Okay, now this is an idealized system. Now, what we did in the examples, once we have an idealized system, we divided the entire system into small subsystem, entire domain into small subdomains. Okay, let us divide this. So now in this case, let us divide the entire domain into small triangles, finite number of triangles, each triangles having finite sizes. Okay. It's not necessarily that we have to do it only with triangle. I am doing it for demonstration purpose, and we will see shortly that we can divide the domain. There are other shapes available through which we can divide the domain. Okay. Now, once we have divided the entire problem into small sub-problems, small triangle in this case, then next is, see, these are essentially the building for, at least for this problem and this domain, these triangles are the building blocks, right? It is very similar to the example of calculating the circumference of a circle. Their building blocks were the linear segment, piecewise linear segment. Every piece essentially the building block of that entire circle. Here also, it is these triangles are the building blocks of this domain. Okay. Then what we did in the case of the previous example, we calculated the length of each segment. Okay. So here we calculate whatever we require. Suppose the governing equations we have, so we write these governing equations, we satisfy the governing equation for every sub-problems. Okay. Now, in the previous case, our problem was, another thing I would like to emphasize here, you see, what essentially need to be satisfied. You see, in the previous case, in the case of determining the circumference of a circle, our objective was to find out the total perimeter, right? Length of the entire perimeter. So therefore, when we divide the domain into small subdomain, it should be ensured that for every subproblem, we have that information. We know the length, because once we know the information of every subproblem, then only we can combine this information. At least we can combine the information of all the subproblems to get the information of the entire system. In the case of determination of area as well, we divided the entire shape into small squares. For every squares, we know the area, so that add all the areas and get the area of the entire shape. Similarly, here we need to once it is discretized, once it is divided into these problems, the governing equations that we need to See, our objective is to satisfy this governing equation over the entire domain. That is our problem, right? So if the governing equation satisfied over the entire domain, means at every point, at every subdomains, this governing equation need to be satisfied. Okay. So next is for all, in every triangle, every subdomain, these governing equations need to be satisfied. Okay. Once we have now, so these elements, these triangles are essentially called. So if we take any triangle, for instance, if we take any triangle, these triangles are called element. Okay. Element, or to be specific, finite element. Finite element, but very often we call it just element. Okay. Now, so once we satisfy the governing equation at every element, then information from one element should pass to other elements. Okay. How it is to be done? You see, consider these two elements. Suppose this is element number 1, this is element number 2. Okay. Okay. Before that, now this is called element, and these points are called, these corner points are called node. Okay. Now consider these two elements. This element is like this, and this element is like this, right? So this is the nodes of these elements, and this is the nodes of these elements. Okay. Now these two elements, element number 1 and element number 2, they are connected with each other at the corner, at the node. So when we satisfy expression at the governing equation at one element, governing equation at another element, the passing of the information has to be through these common nodes. Okay. Now once we write the governing equations, for all these elements, all these triangular elements in this case, and the next step what we did in the case of previous example, we combine them, we assemble all these line segments to get the perimeter. Here also we need to assemble the information of these elements to get the information, to get the equations for the entire system. And once we have the equation for the entire system, then it is to be solved. Okay. Now, so let us now write the different steps that we follow in finite element method. So this is the premise, this is the basic philosophy of finite element method, but let us understand it through. Okay. Now I will come to it. Is, you see, in the previous examples also, if we keep on refining if we keep on increasing the number of segments, we get better accuracy. It is same for here also. This is your idealized model, and this is called a finite element mesh. And so once you solve, you get a solution for this. So you get a solution for the, you get, yes, you get a solution for this, say approximate solution for this, say approximation 1. You get an you can then refine the mesh. You get approximation 2. You can further refine the mesh, and you get approximation 3, and so on. And then you will see that if your actual result is somewhere here, then you will slowly converge to the actual result with different level of approximation. And then we need to choose at what point we have to stop, because if we find that the approximate solution we get that is close enough, that is acceptable for in the context of this problem, that is fine with us. Now let us then see what are the different steps, the basic concept of finite element method. You see, this is the basic concept of finite element method. Okay, what is done here? First, we have a problem domain. Problem domain means the idealized domain. Okay, this is an idealized domain. That is always the starting point of analysis. Okay, now next, the mesh generation. Next step is the mesh generation. Mesh generation means the representation of the problem domain as a collection of several subdomains, or in this case as a collection of several elements. Okay, now that is the step, the step 2. Then what we do, once we have that collection, once it is divided into finite elements, okay, these are called finite elements. This triangle in this case are called finite elements. Once we have these finite elements, then we need to write the element equations, governing equations at the element level, and that is called element equations. Okay, we'll give you the demonstration of what is the element equations and all. So this step is called element formulation. Means, see, this is the most important step. In fact, you will see that most of the discussion in this course will be on how to constitute, how to form these element equations. Okay. So once we have the equations at the element level, then what is to be done next? Then these equations need to be assembled. Once we assemble these equations, then we get the equations for the entire system. This mesh generation is also called discretization. Discretization means now it is essentially a collection of some subdomains. Okay. Now, once we assemble all these element equations, we get the discrete equations for the entire system. And once we have that system of equations for the entire problem, then we need to solve it and then finally see the solution. As I just now said, most of as a concept, it looks very straightforward, right? And not just that. If you think, then these steps you have been following in many problems, right? Not just, and to understand this concept, you really do not have to be an engineer. Most of the problem we come across in daily life, that may not be the engineering problem, right? Most of the things that we do in our daily life, you will see that in back of our mind, we follow similar approach. We break the entire problem into small problems, try to address each sub-problem separately, and then add all this information or information of all the sub-problems to get the information about the equations about the entire system, and then finally solve it. So as a concept, it looks very straightforward, but when we actually implement it in problems, that is not as straightforward as it looks like from this slide. And most of the discussion in this course will be to in this step, how to do this. Okay. Now, so as I said, it is not that always we have triangular domain. For instance, if we have so another important thing is this entire exercise, this entire flow. That another reason why in the first class I was mentioning about the popularity of finite element method. See, there are other methods as well, like finite difference method, boundary element method. But one of the reason of popularity of this method. See, this method is mathematically sound. All these things are fine. I mean, there are many other methods which are also based on strong mathematical foundation, but the reason lies in the fact that this method the entire method can be translated into a computational code, right? And irrespective of it's a small problem, large problem, complicated problem, different kinds of element we'll have, this can be eventually translated into computational code. Okay, and you will see, at least in the linear problem, you will see at the end of the day, all these equations that we get, we will be doing some matrix operations. Okay, and that's the reason why you need some idea about, or you need to brush up some idea about matrix algebra. So this is another one of the reasons why this method gains popular. And you see, there are probably more than 400 softwares are written, commercial software, special purpose software. If you put them over the last several decades, more than 400 to 500 softwares are written, programs are written on finite element method. Okay. Now, the same thing, irrespective of whether it is a one-dimensional domain, two-dimensional domain, or three-dimensional domain, same approach can be done. For instance, if I give you an example, suppose I have okay. So let us take an example. So suppose we have a beam, one-dimensional domain. Okay, this is a cantilever beam. Length of the beam is L. Now, same approach we need to do. So divide the entire beam. So this is the entire beam. This needs to be divided into smaller segment. So suppose these are all segments. Okay. This is segment. Now these are elements. These are elements. And these elements are connected. These are nodes of these elements. Okay, so and these elements, suppose this is element number 1 and this is element number 2, this is element number 3, 4, 5, 6. So element number 1 and 2 are connected here. Element number 2 and 3 are connected like this, like this, like this. So from element 1 to element 2, the information passes through this node. From element number 2 to 3, information passes through this node. These are common node. Okay. So once we calculate this, once we have divided the entire problem into small line segment, in this case, a beam element we call it. Now write the equations for all the elements, whatever governing equations we have, whatever beam theory we use, depending on that, whatever governing equations we have. Then once we have written the equations, the governing equation at the element level, assemble all these equations to get the expression, to get the equation for the entire beam. So that is that same thing can be done in case of three-dimensional problem as well. Now let me give you some example of different kinds of element we have in the element library, or find this is not all in whole. For 1D problem, we have this just now the element I showed you. This is two-noded element, two-noded because it has two nodes. Similarly, for 1D problem, we can have three-noded elements as well. You do not have to bother about right now in the very first week why two-noded, why three-noded. Those things we will discuss as we move. Okay. For two-dimensional domain, you can have, in this case, theoretically, you can have a four-noded element as well. Okay. Now 2D problem, we have triangular element. These are all nodes, and this is called three-noded element. Just now the example we have seen in that example, triangular element is used for the discretization. But then we have triangular element with different node number as well. In this case, the nodes are at the vertices of the triangle. But then we can have, along with the vertices of the triangle, we can have the nodes here as well, on the sides as well. We have 6 nodes. That's why it is called 6-noded triangle. We have quadrilaterals, 4-noded quadrilaterals. We can have 8-noded quadrilaterals. We can further increase the node like this. Theoretically, we can have if you want, you can construct an element like this, which is quadrilaterals, but the number of nodes are different. Okay, so these are for two-dimensional problem. Now, for three-dimensional problem, these are the different elements available. This is called tetrahedron, 4-noded tetrahedron. This is 10-noded tetrahedron. Then we have hexahedron elements, 20-noded, 8-noded. Then pentahedron, 6-noded element, 15-noded elements. Now see, these elements alone cannot carry any information. You see, now in the first class we have discussed that finite element has application in almost every branches in engineering and science, right? Now, the premise of finite element, the basic philosophy will remain same irrespective of the problem you apply. Okay, make it and then get it. And then when you break it, then the elements we use, as far as the shapes are concerned, these are the common shapes we have. But then once we discretize it, once we have divided the entire domain into elements, the element level equations need to be written. Okay. Now, these equations are essentially the governing equations of the problem. Now, the governing equations are different for different problems. For instance, if you are doing heat conduction problem, you have an equations, your variables are different, your dependent variables are different, field variables are different. If you are doing a beam problem or a plate problem, your field variables are different. Okay, so what equations you take, what degrees of freedom you have, what are the field variables, those are different for different applications. So now these elements alone, these shapes cannot give you any information. Along with these shapes, at every node, these field variables need to be defined. For instance, the same quadrilateral element, the same shape element we can use for heat conduction problem, we can use for, say, 2D elasticity problem. Shapes in both the cases are same, say 4-noded quadrilateral or 8-noded quadrilateral. But then information at the node in case of elasticity problem and the information at the node in case of heat conduction problem, those are different. Our variables are different. Okay. So these elements along with the information at the node gives you the complete picture. Okay. Now, so those things we'll discuss when we see the application of this finite element method in different area. Now, so finally, let us see some. Yeah, these are some just for the visualization. You see, for different problems. For instance, the first problem is you have a solid object and a spherical ball is impacting on that surface. So here the entire surface and the spherical ball is discretized. In this case, is a 3D bracket. The bracket is discretized. Here also it is the human bone, femur bone, and this, if you want to analyze it, this is discretized. For all these three these are 3D problem. For all these discretization, these elements are used. Okay, this is the elements used. Then we see some 2D problem. For instance, this is a 2D bracket and this is discretized with a two-dimensional element, triangular element, but we could have discretized with, say, quadrilateral elements as well. This we could have discretized this 3D problem with say tetrahedron as well. For instance, in this case, these are the bracket, this is the jack you have already seen. So these are all discretized using this tetrahedron element. Okay, but this is not an all in whole. It depends which problem you use and what elements to be used. That is also an important aspect of finite element method, and those aspects we'll discuss in subsequent lecture. Okay, so this gives you the basic idea of finite element method, at least the philosophy of the finite element method. And then next, next 11 weeks probably we'll be discussing how to translate this idea into a method. Okay, based on this idea, we'll try to form a method and then apply this method to different problems. Okay. Now, that will start from week 2. Next class, what we do is, you see, element level equations need to be formed, and that is essentially the governing equations. So the governing equations need to be satisfied at the element level. Okay. And then assembling and then final solution. But for some simplified system, without using the equations directly, we can form these element level equations, and that is called direct approach. And direct approach you have already used in your structural analysis course. For instance, direct stiffness method. You have done essentially that. And you look at, if you have a background in direct stiffness method, then please try to see the similarity. In direct stiffness method also you did the similar thing. The building frames, you have written member stiffness matrices for different members and then assemble it to get the stiffness matrix of the entire frame. It is essentially the same, but in a more general way we do it. Okay, so let us stop here today. So next class we'll see, just quickly review the direct approach. Thank you.